Hi everyone. Welcome back to another video. So we have section 4.10 today. This is antiderivatives. So this is going to be kind of a complete change in mentality from what we've been doing so far. I mean, as you can tell from the title, this is antiderivatives. This entire course so far has been about derivatives. So we're doing the opposite essentially of a derivative. So this is going to require you to think kind of the opposite direction that a derivative would go. And you'll see exactly what I'm talking about once we actually get to the idea of a derivative, of an antiderivative. So this is something that's usually covered at the end of a Calc 1 course. If you are expected to take a Calc 2 course, Calc 2 is all about antiderivatives, essentially. So if you think about kind of the order of calculus, right? Pre-calc is just kind of all of the basic knowledge, the foundational knowledge. Calc 1, sorry if you can see a little thing moving over there. That is my cat. Calc 1 is all about derivatives, and then Calc 2 is all about antiderivatives. But it is important to kind of touch on the idea of an antiderivative at the end of a Calc 1 course. So that's what we're going to be doing. From here on out, we're going to be talking about antiderivatives and the idea of how they relate to like area and their applications. So let's first get a definition of what it means to be an antiderivative. So a function is an antiderivative. So a function f, so we'll call it capital F for the antiderivative of the function lowercase f if capital F prime, so you take the antiderivative, you take the derivative of that, and you just get the original function. So what's that telling us? That is telling us that if you take the derivative of an antiderivative, you get back to the original function, which seems to make sense, right? I mean, if you think about anti and then the regular thing, they kind of seem like they would cancel each other out in just word form in general as well. All right, and that's for all x in the domain. So now we can consider the general form of an antiderivative. So let f be an antiderivative of lowercase f over some interval. Then we have kind of two statements here that we'll want to look at. So for each constant c, so this is capital C, this will be a very, very important concept throughout the rest of this course. And then again, if you take Calc 2, this is something that you're going to have to remember. This pesky little plus c is something that a lot of students will forget, and it's a very easy way to just lose points on exams and homeworks and everything like that. So for each constant c, the function capital F of x plus c is also an antiderivative of f over I. So what that's saying is capital F is an antiderivative, but also capital F plus c for some constant c is an antiderivative as well. We also have that if g is an antiderivative of f, so maybe you have two valid things that are antiderivatives, then there's a constant c for which g is equal to f plus c over I. All right, so in other words, the most general form of an antiderivative is f of x plus c. And this right here is really going to be the gist of what we're talking about. So when we're looking at an antiderivative, we want it to be the actual antiderivative, which is going to be your f of x, but then you have to consider that there may or may not be a constant that you have to add at the end. And we'll see that this actually makes a lot of sense because if you consider that this is the opposite of a derivative, and that if you take the antiderivative of a derivative, or alternatively, the derivative of an antiderivative, you get back to the original. Well, if you take the derivative of f prime, as we saw on the slide before, that gives us f. If you take the derivative of a constant, that goes away. And so that does show us that f is equal to lowercase f is equal to capital F prime because the c just disappears when you take a derivative of a constant. All right, so here's an example. This is a bunch of variations of the same general equation. So as you can see, kind of the base of this equation is going to be the 6x to the fourth minus 7x squared. This was using Desmos. I absolutely love Desmos. So if you're ever kind of curious about what things look like or want to use a good online graphing calculator, of course, we don't use calculators in this course, but if you're just trying to like learn or something like that, I encourage you to look at an online graphing calculator. Specifically, Desmos is great, free, awesome. So as you can see, every single equation here has the same 6x to the fourth minus 7x squared. And the only thing different is going to be this term at the end. It's going to be your plus c term. It's going to be whatever constant you're adding. And as you can see from the graphs, as they're all color-coded here, they all have the same exact shape. The only difference is going to be the location that they are on our actual axes. So they hit the y-axis in different locations, and of course they have different x-intercepts by default. So what is the derivative for each of the functions listed above? Well, if we look at any of these, since they all have the same first term, the derivative is easy, right? 6 times 4 is 24. X to the third minus 7 times 2 is 14x. But then the derivative of any of these constants is just going to be 0, right? Derivative of 2 is 0, derivative of 1 is 0, there's nothing here. And then the same, these are also 0. So the derivative of all of these functions are just going to be this function right here. So as you notice, they all have the same derivative, which is the exact idea of why we have to add a plus c term, because we may be given this from the start, this y prime, but we don't know if we're trying to go backwards now from the derivative to the original function, which one is actually the valid function. Maybe we're actually looking for the one that has a +1 at the end, but we don't know that unless we're giving like some initial conditions, unless we're given more information. So we have to indicate that there may or may not be some c value at the end that we would have to take into account that would kind of dictate where we are on our y-axis and how that impacts our x-intercepts and everything like that. So what is the most general antiderivative for y prime? That is going to be this right here, but plus c. So anytime we're looking for an antiderivative, so the antiderivative of a derivative is just the original function, so we'll just call it y. So we can say that's going to be 6x to the fourth minus 7x squared, but then we're just going to say plus c. And I do also want to note plus c is the indicator for positive and negative functions. So you're not ever going to want to say like minus c, because that will take into account the negative functions as well. So plus c could be -2. All right. So let's go ahead and kind of think backwards now. So for each of the following functions, find all antiderivatives. So while we will develop a few techniques, of course, like I said, if you go into Calc 2, you'll have significantly more techniques. But while we'll develop a few techniques for computing antiderivatives, there are just general ways that we can think about antiderivatives of specific functions. So what I want us to do to compute antiderivatives, especially of these right here, is we are going to consider the derivative. So we're going to ask ourselves, well, what would I have to take the derivative of in order to get this as the function? That's exactly what we're going to have to do, because then if you take the antiderivative of that, you get the derivative, and we would confirm all of this. So let's take a look at A first. So the question we'll ask ourselves is, what do we have to take the derivative of? Oh, to get f of x. And that will give us our solutions to get f of x. So if we're looking at 3x squared, what we know is that for a general power rule, obviously you take the derivative with respect to x of some x to the n. The power rule says that it's n times x to the n minus 1, right? So if we want to have something where we take the derivative and we get 3x squared, we know this 3 was probably going to be the exponent, right? So this implies that our capital F of x, because this is how we'll denote that this is the antiderivative, well, this 3 is probably going to be the exponent, because that's what this tells us. We take the number in the exponent and we bring it down. So of course, we'll still have the x. We can rewrite that. And we have this here. And then we have to say, well, do we have any number out front? Well, if we just try to take the derivative of this function right here, bring the 3 out front, subtract 1 from the exponent, we get 3x squared. So in fact, we do not have to adjust the number out front of this at all. What we do have to do, however, is we have to add a plus c, because we don't know if there could be a number being added or subtracted to this. Because if we take the derivative of that, again, it just goes to 0, and that wouldn't be indicated in our derivative function. So this is the most general antiderivative of A. And we were able to do that without using any rules, just by using our reasoning and our knowledge of derivatives. All right, what about 1 over x? So this is one that you are just going to have to like memorize. Again, we are going to have a rule for especially things that look like A for power functions. I know we have a power function, like I said, of the derivative power function. We will also have a power rule for integrals or for antiderivatives. We'll be using those two terms synonymously, antiderivatives and integrals. So we'll have a power rule for antiderivatives as well. But for 1 over x, we don't get to use that because 1 over x is a very special derivative. So if we think about what we have to take the derivative of to get 1 over x, it's not going to be something that's just like just an x function. What we actually do is we have to take the derivative of the natural log of x. So remember, if you have the ln of x, take the derivative, you get 1 over x times the derivative of whatever's inside of the natural log. Well, since this is just x, we're just going to leave it as x. So for b, we're going to say f of x equals the natural log of, but something that we notice is that this x here isn't necessarily positive or negative, it's just x. So theoretically, this could be positive or negative. But what we know about our natural log function is that we can never have a 0 or a negative in our parentheses. Obviously, this can't be 0 because we can't divide by 0. So these are either negative or positive values. So instead of putting parentheses like this, we have to indicate that we can only have positive values. And the way that we do that is with absolute value bars. And we can put absolute value of x like that. So the antiderivative of 1 over x is the natural log of the absolute value of x, because otherwise you could theoretically have a negative number in there, which would be an invalid equation. And of course, we have to add c because we don't know if there's a constant being added. All right, for c, this is a cosine function. So we know right off the bat, sine and cosine, when you take the derivatives of them, you get the opposite function, but maybe with a sign change. But sign change, not sine. Always have to clarify. So for cosine, we know that obviously our capital F of x is going to have to be something with a sign, right? Because that's just going to be any antiderivative or derivative is the opposite function. But now we have to consider, do we have to change this sign? Is this a positive or a negative? Well, we just have to consider what the derivative of this would be right here. So the derivative of sine is positive cosine, which is in fact positive cosine right here. So we don't have to adjust this sign. And in fact, what you'll notice is that we know the derivative of cosine is negative sine, which means that the antiderivative of cosine is positive sine. Likewise, if you have the derivative of sine being positive cosine, the antiderivative of sine will be negative cosine. So they kind of flip signs, sign signs, when you're looking at the antiderivative, but the actual trig function will stay consistent when you're taking the antiderivative. And of course, we have to put plus c. It would be incorrect without plus c. All right, lastly, we have d, which is e to the x. So for e to the x, we have to, again, consider what do we take the derivative of to get e to the x out? And we know the derivative of e to the x is e to the x. Since we know the derivative of e to the x is e to the x, what that tells us is that the antiderivative of e to the x is also just e to the x. Of course, if we had a number in front of it, or a number in our exponent here, it would be slightly different. You would have to adjust the number in front of the e to the x, but that's not the case. So since the derivative of e to the x is e to the x, the antiderivative is also e to the x. So our antiderivative is simply e to the x plus c. All right, now I did mention the term integral, so I just want to clarify exactly what I mean. So we, like I said, use the terms integral and antiderivative kind of synonymously, but there is a slight difference between them. You'll probably never be tested on that or never be required to reproduce the definitions or the reasons why they are different. But a lot of times when I talk about them, a student's first question is, well, what's the difference? So I just wanted to mention vaguely what the differences are. It's very nuanced. So we'll look at the formal notation. So obviously this is the formal notation for an antiderivative. The symbol here, so this here, the whole thing here, this is the antiderivative. But this little symbol I have not yet named, right? So this just kind of looks like an elongated S, and it is just an elongated S, but this is called an integral sign. So when I say take the integral of, what I mean is we're going to use this integral sign and we are going to take the antiderivative of a function. So if we're looking at, say, the integral of f of x dx, this dx represents what variable we're taking the antiderivative with respect to. This is called the indefinite integral. And this word indefinite does in fact matter. So I'm going to highlight this. We have a difference between indefinite and definite integrals. And in fact, we're going to have a whole section on definite integrals in two sections. Two sections. So we will talk about definite integrals and how to compute those. But right now we're just talking about indefinite integrals. And so when you take an indefinite integral of something, this is when you add plus c to the end of it. So sometimes we'll say take the integral of, sometimes we'll say take the antiderivative of. Typically, integral is a little bit more for like the broad sense, and taking an antiderivative is the actual act of like doing this thing. So saying take the integral is kind of setting it up, and then the antiderivative is the act of actually like computing the value. Um, it's very nuanced, and there's not a whole lot of a degree of separation between the two. I encourage you to look it up if you're still a little bit confused, because there are definite integrals, and sometimes the internet will say that an integral is like the definite form and an antiderivative is the indefinite form, but we have indefinite integrals, so that's not exactly the case. So it's kind of confusing, but just know that if we say antiderivative or integral, we're pretty much just asking you to do the same exact thing, just a different way of saying it. But this is, in fact, an integral sign. This is going to look like this when you draw it. All right, so now let's formally define what it means to be an indefinite integral, which I kind of already have. So here we have the term indefinite integral, denoted the integral of f of x dx. And the most general antiderivative of f is going to look like this right here. The integral of f of x dx is capital F of x, which is, again, the antiderivative of the lowercase f of x plus c. So this is exactly what we were talking about earlier, but now we've kind of given a name to it. Now I can also define two other things. So similar to how sometimes I'll refer to like the thing in the parentheses of a natural log or a sign as an argument. That's like the formal definition of what that is. Um, or say the thing underneath the square root is called a radicand. We have this f of x right here, the thing that we are taking the antiderivative of is called the integrand. So if you ever see that terminology, the f of x is the integrand, that just means that that's the thing that we are taking the integral or antiderivative of. And then for the dx, the d will always stay the same. That just represents the fact that we are taking the antiderivative of this function, and you always have to have the d, whatever it is at the end. Otherwise, it's not like a complete antiderivative statement. But the x may change depending on what variable you are taking the antiderivative with respect to. So here the variable x is called the variable of integration. So you may have y, and this may be f of y, and then y would be your variable of integration. So either way, no matter what your variable is, maybe it's t, then t would be your variable of integration. It's very important that we note what the variable is here, especially, again, if you go into any higher levels of math, especially if you go into Calc 3, where we deal with three-dimensional calculus and you're doing things with multiple variables. It's multivariate calculus. You will have to rely very heavily on exactly what you're integrating. And it becomes much, much more important, because right here, obviously, we're just going to have a single variable. And so obviously you're integrating with respect to that variable. A little bit further down the line, you may have two variables. And so it'll be a little bit more important to recognize which variable you are taking the integral with respect to. Given this terminology, the act of finding antiderivatives is called integrating. So same exact thing, we'll say, integrate this, you are integrating this. It's all used synonymously. You just wouldn't say like you're anti-deriving. That's not usually something that we'll say. So we'll say that you're integrating f. All right, here's another example. So for a function, f and its antiderivative capital F, we know that obviously capital F plus c is going to be your antiderivative, where c is any real number, positive or negative. You can have any c value. In fact, you can look at many c values altogether, And if you consider many C values at once, you can look at like the family of antiderivatives. And so that's exactly what this is right here. You're going to look at a family of antiderivatives. This isn't going to be super important for the rest of the course. This is just kind of to further your own understanding. So for example, since x squared is a derivative of 2x, which we know because if we consider that in order to have a number out front, say this 2, we would have to take this and bring it into our exponent. And then if we tried taking the derivative, we would in fact get back to this, right? So the antiderivative of 2x would be x squared. Then we know the antiderivative of 2x is going to be x squared plus c, because we always have to add c when we don't have any initial conditions. So the collection of all x squared plus c would just look like this. So again, this is just more for your own understanding. I'm not going to ask you to create like a family of functions or anything like that. All right, so now we get to the rule that I mentioned, the power rule for integrals. So this is something that you're definitely going to want to memorize. And this is very important right here for all n not equal to -1. So what we mean by that is that, say x, we have x to the -1. Well, what is this actually? We know that we can rewrite this by negating the exponent and changing the part of the fraction it's in. So we can write this as 1 over x, which is exactly the example that we looked at earlier, because we know the integral of 1 over x dx is going to be the natural log of the absolute value of x. So we cannot use the reverse power rule on this, because if you did, what you would get is dividing by 0, and that would be invalid. So we know that this has to be the natural log of x. So this is a very special case. This rule will work for every other value, though. So what that rule says is if you have some exponent, you go up a power in your exponent, and then you divide by that power. And that's actually how I typically like teach it and how I will think of it even now in my head. Teaching it for years, I still say this in my head every time. The way I was taught, instead of memorizing the notation, was this: up a power, divide by that power. All right, so as you know, I try to give you guys as many like little tricks to help you remember stuff as possible, right? The quotient rule, we have a little saying instead of having to remember like F's and G primes and all of that. We just have something to remember it. This is how you're going to remember this. Up a power, divide by that power, and then of course add C at the end. That's just a given. All right, so let's go ahead and practice. So here we have the integral of x dx. First of all, what's important to note is that if you don't have an exponent explicitly written, you have to assume that it's 1. So we'll go ahead and use the up a power divide by that power rule. Up a power, so I would always write my base here, maybe put a fraction bar. Up a power is going to give you 2, divide by that power is going to give you 2, add c. And that's it. That right there is your integral. It's very simple and very easy to compute as long as it's just like a simple variable term. It's nothing too complicated. If you have a number out front, say this was like 3 or 4x, you would put that in our numerator and then still do the same up a power divide by that power. You may just want to try to simplify that afterwards. So like if this was 4x, you'd have a 4 up here, and then you can turn this into 2x squared, for example. All right, this one, same thing. We want to go x. We know it's going to be a fraction. Up a power, so 2 plus 1 is 3. Divide by that power. Put a 3 down there. Plus c. Very straightforward. Here, x, we know it's a fraction. Up a power is 4. Divide by that power. 4 plus c. X to the n. We may not know what n is, so x over, well, we know up a power is just plus 1. Divide by that power, well, that's n plus 1. Plus c. So even if we don't know the number, we can still create the general form given any n value. Again, that's not -1, because if it was, we would have a natural log instead. All right. So for these, this is just kind of for your own understanding. If you want to write them down, you can. I put these in here so that you can see some integrals and derivatives and their relationships a little bit better. There's going to be a lot of them. There's 3 slides of these. That's a lot to write down. So this is more so just for your own understanding. So, for example, looking at like a derivative of a constant being 0, what we have to consider here is if you're taking the indefinite integral, so the derivative of a constant we know is zero. The indefinite integral of a constant is going the other direction. So now what we would want to do using a constant is we still want to kind of tack on a variable there because you don't have a variable. So what we would do is we'd call it x to the zero because we know anything to the zero is one. And then we can use the upper power divide by that power rule. Well, 0 plus 1 is 1. Anything divided by 1 is itself. And so your answer is your constant times x plus c. This is the power rule that we just discussed. Obviously, the derivative of the natural log of the absolute value of x is 1 over x, which tells you that the integral of 1 over x is the natural log of x. So what this is doing is showing you kind of the forward direction and the backwards direction, if you will. So that's what I was mentioning earlier about like changing directions or like changing the way that you see things, the shift, because you're going this way one time for a derivative. So this is the derivative, but then this way for the antiderivative. So it's really about changing your perspective a little bit. Here we've already done this one. Obviously, the derivative of e to the x is e to the x. Therefore, the integral of e to the x is also e to the x. Like I said, there's a lot of them. I don't suggest writing them all down. This is just for your own understanding. As we saw, the derivative of sine is cosine. So if you integrate cosine, you get sine. Essentially, you're just going to take this side and you're moving backwards. So I encourage you to just maybe glance through these. I'm not testing you on your knowledge of memorizing all of these. And in fact, if you ever were asked about these, you would be expected just to like know the derivatives from earlier, and you should be able to reproduce this without having to like memorize antiderivatives necessarily. These I'm not so pressed about because that's cosecant, secant, and cotangent. And to be honest, I don't even have the derivatives of those memorized, so I don't expect you to either. All right, and then these are some inverse trig values. Um, so a lot of times we can see inverse trig like this. When we were taking derivatives of inverse trig, we used implicit differentiation. So our derivatives looked a little bit different, but there is a way we can rewrite it to make it look like this. So this is just something to keep in mind because this is something that you will probably see in Calc 2 if you have to take it. So be familiar with these right here. Maybe not so much a secant one, but definitely the inverse sine and the inverse tangent especially. So if you ever see 1 over 1 plus x squared, know that that's arctan. Because that does come up. There's something called trig substitution, and this will come up when we have to do stuff like that. Not in this course, but in a further course. All right. So obviously we've now talked a lot about indefinite integrals. We have that this is the form. We don't have to rewrite it. So what we have to do though is kind of verify what we've been talking about. So we want to verify that f prime, capital F prime, is actually equal to lowercase f. So let's go ahead and verify that what we've been talking about, what I've been telling you is true this whole time, is actually true. Promise I'm not lying. But let's make sure I'm not lying to you. All right. For each of the following statements of the form integral of f of x dx equals capital F plus c, verify that the statement is correct by showing the derivative of capital F is equal to the derivative, just equal to the regular function. All right. Let's take a look at A. So what we're doing is we want to leave the regular function, our integrand f of x, and we want to take the derivative of the capital F of x, which is going to be your right-hand side. So we have the derivative with respect to x, because we're looking at it with respect to x here, of let's just look at the right-hand side, because that's what we're looking to show, x squared over 2 plus e to the x plus c. Well, the derivative of this thing is going to be, this is power rule, so bring the 2 out front, except that if you do that, 2 times over 2 is just going to be x. Subtract 1, you get 1, so I don't have to write that. Plus the derivative of e to the x is just e to the x, and the derivative of c goes away. So we get that the derivative is x plus e to the x, which is in fact what this integrand is right here. So we verified this one. Let's take a look at b. So b, we're looking at the derivative with respect to x of x e to the x minus e to the x plus c now. So we've added a step because what we should recognize from early on, this is like 3.3 differentiation rules, is x times e to the x is a product of two different terms. So we'll have to use product rule on this one. What we remember from product rule is that it's first times the derivative of the second plus second times the derivative of the first. So let's go ahead and do that. first, that's x, times the derivative of the second. Derivative of e to the x is just e to the x, plus second, which is e to the x, times the derivative of the first. Well, the derivative of x is just 1, so I don't need to write that. All right, next, minus e to the x, so the derivative of e to the x is just e to the x. And then the derivative of c goes to 0. Now we can simplify this because as you see, this does not look exactly like x e to the x. But what you recognize, so here, this is x e to the x. This is e to the x minus e to the x. So these two terms just disappear. So we do, in fact, have x e to the x in both spots. So we've confirmed that this statement is true. So I promise I'm not lying. All right. Now we can talk about what happens when we have maybe multiple functions or maybe multiple terms within a function. So right now, the only thing that we've looked at is a single term. So maybe I said integrate x cubed. But what if it was x cubed plus x squared? Well, this is where we would consider one to be f of x and one to be g of x. So what this says is f and g are both going to be antiderivatives. So capital F and capital G are the antiderivatives of f and g. And k is just any number. So what this says is if you have the integral of f of x plus or minus g of x dx, then your integral is capital F of x plus or minus capital G of x plus c. So what this tells us is that we can integrate each term separately. And so this is the same thing. This implies, so an arrow like this means implies, the integral of f of x dx plus the integral of g of x, or I'll go plus or minus since that's what we had, dx equals capital F of x plus or minus capital G of x plus c. So you can also break it up like this if you'd like. So you can break up an integral with pluses or minuses. You cannot break up an integral in terms of multiplication or division. So for example, if you have the integral of x e to the x dx from the last slide, you cannot say that this is the integral of x dx times the integral of e to the x dx. This is not valid. You'll find out in Calc 2, if you take it, how you would compute this, but this is not how you can compute this. So absolutely no way to compute that like that. All right, and then we also have this rule. This is the constant multiple rule that says if you have the integral of some constant times your function, you can actually technically pull out your constant before you even take the integral. So this could be k times the integral of f of x dx, which would then give you k f of x dx like this. So you really just kind of bring the constant along for the ride, very similar to how you would bring the derivative along for the ride, the constant in front of your derivative. All right, so let's go ahead and do some examples now with multiple terms. So this first one, we are just going to use the properties that we talked about earlier. So as you see, this is a bunch of terms with just a single variable in it. So what we're going to do is we're going to integrate each term separately. Because it's separated by pluses and minuses, we can do that. So the integral of this thing equals, well, the integral of each thing separately. So the integral of 5x to the third, what I'm going to do is I'm going to write the 5x and I'm going to put a fraction bar. And then we're going to use the power rule. All right, up a power, so that goes to 4, divide by that power, so 4. Keep the minus, keep the 7 in the numerator and the x, put a division sign. We see the exponent here is 2, so up a power gives us 3, and we'll divide by the 3. Plus, here we have a 3x over, well, this is technically a 1, so up a power gives us 2, divide by that power gives us 2. For this 4, what we'll have to consider is that 4 is equal to 4x to the 0, as we know, because x to the 0 is just 1. So this is going to be plus 4x to the 1 over 1. Essentially, anytime you just have a constant and you're taking the integral of it, all you want to do is stick whatever variable you're integrating with respect to onto that constant. So this just becomes 4x essentially. And then you'll say plus c. There's really no way of simplifying this. Obviously, 5 over 4, 7 over 3, 3 over 2, those are all irreducible fractions. This 4 over 1, you could just write as 4. That's the only thing you could simplify, but for the sake of time, I'm not going to rewrite this whole thing. If this was, for example, 12 over 4 or something like that, I would probably rewrite it just to make it look a little bit prettier. All right, this next one, we have something that looks kind of funky. So as you see, we have addition, which is good, but we have division, which is bad. I mentioned earlier that we cannot take the integral of division, but what we can do is try to adjust the function so that there's no division left. So because we're dividing by an x and all of these terms just have an x, what we're going to do first before we integrate it is we're going to rewrite it so that we are just adding and subtracting terms. So we're going to say this is equal to the integral of, well, we remember if we're dividing by a single term, we can actually divide each term by that term. So I can say this is the same thing as the integral of x squared over x plus, I'm going to rewrite this cube root of x as 4x to the 1/3 using our power over root rule, over dividing this by x as well, dx. So all I've done is rewrote it so far. Again, I'm not going to do anything yet. I'm going to still write my integral sign, and I'm going to simplify this now. X squared over x gives me x plus, and then this I'm going to simplify as well. So 4, and we remember this is an exponent of 1. 1/3 minus 1 is the same as 1/3 minus 3/3. So it's going to be x to the negative 2/3 dx. Now, once I've written it like this, it's just in terms of addition, so we can use the power rule. So because this is an x to the 1, we can have x fraction bar up a power is 2, divide by that power is 2. This right here, it might get a little bit funky. So this is 4x up a power, so negative 2/3. I'll write this over here. Negative 2/3 plus 1 is the same thing as negative 2/3 plus 3/3, which is positive 1/3. So this will be 4x to the positive 1/3 divided by 1/3. And then we have to add c. Now, this you should simplify. Never leave it as this complex fraction. This is just not something that we like to do. So in the earlier part of the course, I said don't simplify anything. When it comes to this, we do want to just simplify a little bit. So we'll say this is still x squared over 2. When you divide by a fraction, we can use keep, change, flip. So keep this, change this, flip this. What this actually becomes is going to be plus 12x to the 1/3 plus c. All right, so you do want to adjust this just to make it look a little bit better. So C here, what you'll recognize first is I want to rewrite this. So what I'm going to do is I'm going to pull this 4 out front. This is by the constant multiple rule that I can do that. So I'm going to say this is equal to 4 times, that's a really bad integral. That doesn't look like anything at all. 4 times the integral of 1 over 1 plus x squared dx. Now this you can't just divide, right? So you can divide both terms in B by x, because that's just how fractions work. Now you can't do that here, but what you may recognize is that this is something that I said you probably should know. Let's see how far back it was. Right here. So you may recognize 1 over 1 plus x squared. This is something that you should just keep in mind. You may see this quite often. The integral of 1 over 1 plus x squared is arctan of x. So that means that this is equal to, keep the 4 out front, but this is arctan of x plus c, of course. This last one, what we're going to want to do is we are first going to want to try to simplify this because there's no nice way of integrating tangent times cosine. We don't have any rule for that at all. So first we're going to want to adjust this a little bit. So I'll say that this is equal to the integral of, let's rewrite tangent because we know tangent is a function of sine and cosine. So tangent is sine of x over cosine of x. And then we can just say this is still cosine of x dx. Well, now we notice this is cosine divided by cosine, so those two things go away. So this is actually just equal to the integral of sine of x dx, which we know. We know the derivative of sine of x is positive cosine, which means the integral of sine is negative cosine of x plus c. All right. Now we can get to this idea of a differential equation. So let's get this. So a differential equation is an equation that relates an unknown function and one or more of its derivatives. So the differential equation dy dx equals f of x, as we know this is the notation for a derivative of a function, is a simple example of a differential equation. So for example, if you have dy dx equals 6x squared, you can find your original y by integrating both sides. So the integral of a derivative dy dx is just going to be y, and your integral of 6x squared is something we can compute with the power rule. All right, I'm going to write this down a little bit more explicitly. So if you have dy dx equals 6x squared, I'll write it so that we have a little more room. Dx equals 6x squared. And we want to find the just y function. What we're going to do is we are going to integrate dy dx. But what you do to one side, and we need a dx at the end of it because that's what we're going to be integrating with respect to. What you do to one side, you have to do to the other. So that means you have to integrate this with respect to x. And so that's exactly how we're going to be computing this. So this tells us that y, because the integral of a derivative is just the original function, equals the integral of this. So this would give us, so 6x up a power is 3, divide by that power is 3, plus c. Well, we can simplify this. 6 over 3 is 2x cubed plus c, which is in fact what we get right here. It's just a slightly more expanded version of why it is what it is. All right, so this is what it means to be a differential equation. This is how we want to solve these equations. Now, I did mention that we want a plus c unless we have some initial conditions. There are going to be times when we're given initial conditions and we can find c. So now I can formally define what it means to be an initial value problem and what it means to be given initial conditions. So sometimes we want to find a specific function and we're given an x and a y. So we're given a point. We have dy dx equals f of x. We're given some differential function, and the initial condition written however we're given it. This is called an initial value problem. All right. Essentially, what we're going to do, let me see, do I have steps here? No, I don't. Okay. Essentially, what we're going to want to do is solve the antiderivative as usual, then plug in values from initial condition after to find C, and then rewrite with C. All right, so let's take a look at a question. All right, so here's an initial value problem. We see dy dx equals sine of x, and then we're given that y of 0 equals 5. So again, we're not going to consider this y of 0 equals 5 until the very end, once we've actually integrated and we have our y equals something plus c function. So I'm going to write this dy dx equals sine of x, and as you see, I'm giving myself a little bit of space because we need to integrate this and we need to have room to put the integration sign and the dx at the end. So I'm giving myself a little bit of space around each thing that I have here. So integral dx, integral dx, and now I can integrate this. So the integral of y, dy dx is going to be y equals, and then the integral of sine, we again know that the derivative of sine is cosine, so the integral of sine is negative cosine of x. And then this is just going to be plus c. But now that we're given initial conditions, we know what c is. So what we can do is we can go ahead and plug in these values. So we know, obviously, this here is our x value, and this here is our y value, given that y of 0 equals 5. So this tells us that 5 equals negative cosine of 0 plus c. And this, once again, requires us to know our trig values. So this tells us that 5 equals, well, the cosine of 0 is 1. So this is negative 1 plus c. So if you add your 1 to the other side, you get the c equals 6. So what you want to do is you want to take the 6 and plug it back in, and that gives you your final equation. So y equals negative cosine of x plus 6. And now, if you think back to what we were looking at earlier, how you had multiple functions, the family of antiderivatives, this is the very specific one. So out of all of the possible antiderivatives, this is the one valid antiderivative. All right, this is the last one for the day. I know that this video was maybe a little bit longer than the other ones that we've had the past couple of days, but not quite as long as some of the ones we've had. So a little bit of an in the middle. So let's take a look at this last one. This last one is dy dx equals 3x to the negative 2. We again want to find y, so we need to integrate dy dx with respect to x, because that's the variable we have here, which means that we have to do the same thing to the other side. We'll once again save our initial conditions for last. The integral of dy dx with respect to x is just going to be y equals Now, the integral of this, since this is not a -1, we can in fact use our power rule. So we'll have 3x over, let's see, up a power. So be careful with negatives. Negatives are a little bit tricky when it comes to derivatives and antiderivatives. So up a power means -2 plus 1. So that's going to be -1 over -1 plus c. So I am going to rewrite that. So y equals, I'll say -3x to the -1 plus c. But now I'm going to actually rewrite this one more time because we do have to plug values in, and it's hard to compute things that are to a negative exponent. So we're going to rewrite that using the fraction rule. So y equals -3 over x. So by taking our variable and negating our exponent, we can bring it into the other part of the fraction, plus c. All right, this is now something that we can plug our initial conditions into. So what we're told is that x is 1, y is 2. And so what we get is 2 equals -3 over x, which is 1, plus c. Well, -3 over 1, that's just -3. So we can add the 3 to the other side, and we get that c is equal to 5. Therefore, y equals, and you can choose which equation out of these two you want to plug this c back into. Both are valid. I'll do this one. Doesn't matter though. -3x to the -1 plus 5. And that's your final answer. All right, so I know that antiderivatives are definitely kind of tricky because, like I said, you're taking something where your brain was kind of going in one direction and now you're quite literally going in the other direction. So if you have any questions about this, feel free to reach out to me. Um, as always, so we will be talking a little bit more about antiderivatives in the next couple of videos and what they mean in terms of real applications. We'll be talking about definite integrals as well, but we only have a few lectures left, so it's been a pleasure this far in the class. I will give you a little bit more information about your final at some point. If I have not already, these videos are pre-recorded. So I'll see you guys soon.